Okay, children, the second colligative property is elevation of boiling point. Boiling point is one of the physical property. The boiling point of a liquid is the temperature at which vapor pressure equals to the atmospheric pressure. When a non-volatile solute, non-volatile means cannot easily evaporate, non-volatile solute added to a pure solvent at its boiling point, the vapor pressure of the solution is lowered below 1 atmospheric pressure. To bring the vapor pressure again to 1 atmospheric pressure, the temperature of the solution has to be increased. As a result, the solution boils at a higher temperature, that is TB, than the boiling point of the pure solvent T0B. This increase in the boiling point, that is known as elevation of boiling point. Now if you see the graph in your book, temperature, that is pressure, a plot of vapor pressure versus temperature for water and an aqueous solution is given as the vapor pressure of the solution increases with increase in temperature. The variation of vapor pressure with respect to temperature for pure water is only given like this. At 100 degrees Celsius, the vapor pressure of water is equal to 1 atmospheric pressure. Hence, the boiling point of water is 100 degrees Celsius. When a solute is added to water, the vapor pressure of the resultant solution is lowered. The variation of vapor pressure with respect to temperature for the solution is that only given in the graph like this. So from the graph it is evident that vapor pressure of the solution is equal to 1 atmospheric pressure at a temperature TB, which is greater than T0B. The difference between these two temperatures gives the elevation of boiling point, that is delta TB equal to TB minus T0B. The elevation of boiling point delta TB directly proportional to the concentration of the solute particles. M is the concentration of the solute particles. So, delta TB equal to Kb into M. Kb, molar boiling point elevation constant or ebullioscopic constant. If M is equal to 1, then delta TB is equal to Kb. Hence, Kb equals to or T square M of solvent by delta H vaporization. From this, Kb is calculated. So the molar elevation of boiling point of for many solvents given in a book, for water, ethanol, benzene, chloroform, ether, carbon tetrachloride, carbon disulfide, acetic acid, cyclohexane. The value for T0B, Kelvin, and Kb value, everything given clearly in book page number 53. So, the elevation of boiling point also depends upon the concentration of the solute particles, not upon the nature of the solute. So, it's given clearly in book page number 51, 52 and 53. Next, depression in freezing point. Freezing point of a substance is defined as the temperature at which solid and liquid states of the substance have the same vapor pressure. Solid and liquid having the same vapor pressure. So at freezing point, solid and liquid phases are in equilibrium. Solid and liquid both are in equilibrium. For example, the freezing point of water is 0 degrees Celsius. At this temperature, the ice and water are in equilibrium. Ice and water are in equilibrium. When a non-volatile solute added to water at its freezing point, the freezing point of the solute, that is solution, is lowered to 0 degree Celsius. The lowering of the freezing point of the solvent when solute is added is called as depression in freezing point. So, graph, pressure, here temperature. For solvent gets decreased, so solution also get decreased. Graph, because below that it is frozen. The temperature Tk here, then T naught K. This difference is called a depression in freezing point. So, from the graph it is clear that freezing point, that is 0 degree Celsius, as the vapor pressure at this temperature is 1 atmospheric pressure. The vapor pressure versus temperature curve for the solution indicates that the freezing point is lower than 0 degree Celsius. So, the depression in freezing point delta Tf can be expressed as T naught F minus Tf. The depression in freezing point delta Tf directly proportional to molar concentration of solute particles. That is, delta Tf is equal to Kf into m. M is the molality of the solution. Kf, molar freezing point depression constant, cryoscopic constant. So, when m is equal to 1, delta Tf is equal to Kf. Kf is equal to depression in freezing point for 1 molar solution. So, molar freezing point for some other solvent, for example, water, ethanol, benzene, carbon disulfide, chloroform, acetic acid, cyclohexane, ether, everything given in book page number 54. So, if the solution is prepared by dissolving W gram of solute in WB gram of solute in WA gram of solvent, then the molality is M is equal to number of moles of solute into 1000 by weight of solvent in grams. So, number of moles of solute is equal to WB by MB, WB by MB. Therefore, M is equal to WB into 1000 by MB into WA. So, delta TF is equal to KF into WB into 1000 by MB into WA. From this, molar mass MB is equal to KB into WB into 1000 by delta TB into WA. Mass of the solute can be calculated. It is also given clearly in book page number 54.